everyone, how's it going? And welcome to Community Conversations. My name is Liz Yang from the Dependencies Foundation. So Community Conversations is an opportunity for you, the community, to hear from contributors within the internet computer ecosystem, as well as ask them questions live. The internet computer is about to allow Canister smart contracts to transfer ICP, fully opening the doors to DeFi applications. Users will be able to send ICP to a canister that can then manage the ICP, for example, by investing it, by issuing loans, or by allowing withdrawals, all according to the canister's code. Clearly, this requires the users to trust the canister, and the first step towards that is allowing the user to verify which code the canister is running. In this talk, senior researcher Ogden Maric will show you how canister authors can help the users verify this by providing reproducible canister builds. So feel free to take it away.
Thank you, Liz. So I hope you're able to see my screen. Let's try that again. That's better.
Yep, we can see it.
Okay, awesome. So yeah, hello everybody. I'm going to be talking, like Liz said, about reproducible canisters or reproducible canister builds. I'd just like to take a moment to thank a few people who have given input or provided material where much of this talk was sourced from. So Christoph, Claudio, Joachim, and Paul. So like Liz said, the question is, well, why are we interested in reproducible canister builds, and in particular, why now? And the answer is really DeFi. So if you think about DeFi in general, the most popular DeFi platform out there is Ethereum, and at the very, very high level, what DeFi allows you to do is it allows the user to take some Ether and put it into a smart contract. And then the smart contract can manage this Ether in some way. So it can invest it, or it can issue loans, do other kinds of things. And hopefully by the end of this process, the smart contract gives the user back more than they have invested into the smart contract. Okay, so this is Ethereum. Let's see what would happen if we would try to do the same workflow on the internet computer today. So on the internet computer, our smart contracts are called canisters. And unlike the Ethereum smart contracts, which run EVM bytecode, ours run wasm code. So on the internet computer, you could have the user right now put some money effectively into a canister. So put some ICP, which is a native token of the internet computer. However, this is actually where the workflow would stop right now, because as of right now, the canisters are actually not able to manipulate the ICP in any way. So the ledger canister prevents them from further sending the ICP that they own. However, very soon, hopefully, we will actually allow canisters to perform the whole workload. So we'll allow canisters to send ICP to others, and that will allow all the standard DeFi workflows using ICP, and hopefully kickstart the a DeFi economy on the internet computer. Now, if you're a user in this setting here, well, you're giving your money, basically, your tokens or other kinds of digital assets to a program, so or canister. And the very reasonable thing to ask is, well, what's inside of this canister? I.e., what code is this canister running? Right? What is it going to do with my money? And on the internet computer, there's also a sort of peculiarity in a way of the internet computer, or it's a difference at least compared to the other standard smart contract platforms, and that's that the contents of a canister can actually change. So this is not the case on Ethereum. On Ethereum, if you have a smart contract, it is immutable, but on the internet computer, it can actually change, at least in general. So we'll try to see in this talk, basically cover the answers to these two questions. And I'm going to start from the second one. So the question is, well, can the contents of the canister, can they actually change? Like I said, in general, they can actually change. So the internet computer has a concept of a canister controller. And the canister controller can actually change the code of the canister. Now, in general, this is a good thing, and this is why we allow it, because it allows the controller to upgrade the canister code to fix bugs, for example, or to provide new functionality. However, if this canister is controlling other people's ICP or other kinds of tokens, well, in that case, there's nothing preventing a malicious controller in general to just change the program such that it steals the ICP instead of doing the expected and useful workflow, right? So in order to be able to trust that such a canister will actually not just change out of the blue and steal your ICP, the user has to verify that the canister code is immutable, or that it's mutable, so it can change only in a limited number of ways. So this is what users, like I said, this is what they have to check, and how you can check that is with two steps. So first, you can ask the internet computer to provide you some information about the canister, so some status, and this is the DFX command. So the DFX tool has a command, the info command you can see here, with certain arguments or flags that you also have to enter, and you give it the canister ID, and it's going to give you the information about the status of the current canister. And the status is going to show you the list of current controllers of the canister. Now, once you have that list, then you as the user should check one of the following. So either this canister should have no controllers, in which case the canister is immutable, so it can never change code. A variation on that theme is that a canister could have a black hole canister. So there's a particular canister that's called the black hole that is actually itself immutable, and that doesn't change any other canisters that it controls, but it does provide some more useful functionality, namely it allows you to look at the status of the canisters that it controls. So this is a slightly more perhaps user-friendly solution. And a third option that's not available yet, but will also hopefully be coming soon, is to put a service nervous system canister as a controller. So a service nervous system is what we're working on to provide to canister authors. So it's a sort of a version of the network nervous system just for canisters. So this allows you to have a more sophisticated, or to add a sophisticated governance mechanism to your canister, such that you can still, for instance, upgrade code, but only under certain conditions. For instance, maybe the stakeholders of your canister can vote on upgrades and things like that, right? Of course, you could also try to implement the service nervous system yourself. That's another option, but hopefully we can provide that functionality for you. Okay, so this is what allows the user. These are the ways that the user can check that the code cannot change. But once we have that, then we can answer the second question. Well, what code is actually in there, right? So, like I said, it's in a canister. It's always wasm code that's actually running. But in practice, very few canisters will be written directly in wasm. Instead, they will be written in a higher level language that compiles down to wasm, for example, Motoko or Rust. Now, if you want to check what the code is doing, typically you're going to audit the source code. So you're going to, or somebody's going to audit the source code, and a user will usually trust this audit. And obviously now there's a disconnect, right? Because we're auditing the source code, but the canister is actually running some wasm code. And what we really want to check is whether these two things are the same. So how can you check that these two things are the same? So what you can obviously do is you can build the wasm code. So this is something that the user can do, right? The user can take the provided purported source code, build it, get some wasm code out, and now we have to check whether these two are actually the same. And the way we can do that is by taking the hash of the wasm code that the user has built. So this is a SHA 256 hash. And then we can use the same internet computer method that we just saw on the previous slide that is going to provide you some information about a canister. Now we saw that this is actually going to provide you the list of controllers. But in addition to that, it's also going to provide you with the hash of the wasm code, a wasm module running inside of the canister. And then you can compare these two, right? And if they match, then you know that this is really the source code that's running inside of the canister. And if your audit says that the source code is okay, then you can have confidence that the canister is secure, or it's not going to run away with your funds. Okay, so that sounds pretty simple, but there is a snag, and that's in this part here, right? So when you audit source code and you build it, this build process, ideally, it gives you this target source code. But what can happen in reality is that the build process is actually not deterministic, meaning that starting from the same source code, you won't end up maybe at the same wasm that the author produced, but you might end up producing, all different kinds of wasm modules for whatever reason. And the goal of a reproducible build is to actually, change the setting to something like this, where the author can provide a build process that at least most of the time is going to produce the same artifact, so the same wasm code that the author has produced themselves, right? So here I can point out, it doesn't have to be perfect, right? So this is kind of the providing a reproducible build is the responsibility of the author. And if you get to a state where 99% of the time your users, 99% of your users can actually reproduce the exact same build that you were doing and get the same artifact, that's probably good enough, right? So if a few arrows here go outside of the target wasm, that's probably not a disaster. But if it's 5% of your users that can reproduce it 5% of the time, that's probably not good enough, right? Okay, so in the rest of the talk, I'm going to kind of give some high-level explanations and guidelines on how you, as the author of a canister, can make sure that your builds are reproducible, like what are the issues involved and so on and so forth. So let's first take a look at a build process at a high level, right? What does a build do? So generally, you have some kind of a build description. So a build file, this could be a make file, but for Rust, it would be usually something like a cargo toml or something like that. You have some source code, so Motoko or Rust or maybe JavaScript. And you have certain dependencies that your code builds upon. Now, once you have these three things, you're going to invoke a build process, typically using a build tool like mock for Motoko or cargo in Rust C for Rust. And this build process is going to run in an environment. So this is your operating system, right? You have your computer with an operating system and all the tools that you have there. So the build process is going to run in your environment, and based on all these inputs, it's going to produce some kind of an artifact, right? Now, when it comes to reproducible builds, there are a few terms that you might run into, so I would like to explain those quickly. So one is deterministic builds. So this means that given the same inputs, the build process here always produces the exact same artifact. The one problem in practice is that the inputs to the build process are often implicit or can be implicit. For instance, there can be things leaking from the environment most often, like timestamps or absolute file paths and things like that. So another term that's being used and is hermetic builds. So what this means, or at least the way that I understand it, is that the build description should fully describe the input. So there should be no implicit inputs that are coming from the environment into the build process. And taken together, if your build process is deterministic and hermetic, ideally it should also be reproducible. Okay, so now the question is, well, how can we check that our build process is actually deterministic? One tool that can help you do that is called reprotest. So it's a Debian tool, or part of the Debian reproducibility project. It was created in this project. And what this tool allows you to do is essentially take this build process and run it in two very different environments. So it's going to run it in your default environment, and then it's going to do all kinds of things to your environment, like if your build process asks for a timestamp, it's going to give it like different timestamps. It might reorder files, things like that. So it's going to mess with your environment, and it's going to check whether what comes out at the other end, so the artifacts, whether they are the same. And if they're not the same, then it's going to give you a very helpful diff between the two artifacts using the diffoscope tool. Right. So this can help you check kind of the determinism of your build process. We've actually used that on some of our tooling and some of our canisters to see how we fare. So on Motoko, we got positive results for both Motoko and internet identity. However, they were actually limited to a single platform. So on Linux and using reprotest, we didn't find any differences, but we did find differences between Mac and Linux. So these are our results. I'll just come back to the slides here. The slide here. So reprotest, I'll just point out, it allows you to mutate the environment. However, what reprotest cannot really control are the dependencies, and that's the next thing that I want to talk about. That's dependencies. How dependencies affect the reproducibility of your build. So in general, these are a pretty significant source of headache. So if you have a dependency, what you really should make sure is that your dependencies are pinned, meaning that you really specify at least the version of the dependency that you're using, so the precise version. Even better, you can specify the checksum of the code, that source code of your dependency. So most build tools will allow you to do that these days. Furthermore, if you have a dependency, if your code itself is going to be audited, then the dependency itself should also be audited, right? So this adding a dependency basically adds, adds work for the auditors, which I guess is not very surprising. Now, in addition to having to be audited, the dependencies have to have reproducible builds themselves, right? Because the final artifact that you produce is going to include the dependency. So if you, as the author, get one result when building your dependency, but your users get a different result, your entire build is not going to be reproducible, right? And a further point, which might be a little bit less obvious, at first at least, is that in general, you might want your builds to stay reproducible for a long time. So if you are creating a smart contract that you're expecting to run for 5 years or something, and you want people to reproduce your builds, your contract in 5 years, then your dependencies must actually stay available for 5 years, right? And this is not trivial. Usually you will get your dependencies from whatever is the default location in the ecosystem of the tools that you're using. So if you're using JavaScript, Node, you'll probably get things from the NPM registry, or you'll be getting things from crate.io if you're using Rust, and so on. So, and there's no guarantee that these things will stay available. And you have to somehow make sure that they do stay available in order to be able to check the reproducibility of your canisters and audit them down the line. Okay, so we have written up a document that lists documentation in details for authors, how they should go about ensuring the reproducibility of their builds. Now, I won't go into details like which steps you need to take. I'll just summarize the recommendations that we make there. So our first recommendation is to use Docker. As you have seen on one of the previous slides, we actually observed some differences when building our own canisters between different platforms, so between Mac OS and Linux. So to minimize this, we recommend that you use Docker to produce the final build for a canister that you're actually going to deploy on the internet computer. And then in addition to the source code of your canister, you also provide the Docker files that you use to build for users such that they can recreate the same environment that you use for building. Second, when creating the Docker file, you should pin versions of everything. So you should pin the version of the operating system. You should pin the exact version of the build toolchain that you're using. So if you're using Motoko and DFX, you should pin those versions. If you're using Rust, you should pin the your version of Rust-C and Cargo and so on and so forth. Next, when building the Docker images, typically you're going to base these on some images, and you should choose a reputable source for your base images as well as for a toolchain, right? Because you're trying to convince the user that this code really results from compiling your source code. Sorry, the wasm code really results from compiling your source code. So if you're using a shady compiler version or a shady operating system, well, that's going to lower the confidence in the entire process. Next, we already mentioned that dependencies they're kind of a source of pain. So the recommendation is really to minimize the number of dependencies that you have. If you do have dependencies, like we've already mentioned, you should pin them. And you also have to archive your dependencies in some way. So make sure they're available for as long as your canister is going to live or is intended to live. Finally, there are two other things. So you should configure and invoke tools, so build tools the right way. So I won't go into detail there, but in order to, for instance, to respect the pinning of dependencies, you have to invoke, for example, npm a certain way. The details of that are in the document down here, so I won't go over that. And finally, what we mentioned earlier is, you can get reproducible builds that tell you what the canister is running right now, but you also have to make sure that, or the users have to be sure that what the canister is running is not just going to change, on a whim of a controller. So we recommend to use empty or black hole canister controllers for canisters right now, and then consider using the SNS down the line. That's it, actually. So yeah, thanks for your attention.
Great, thank you so much for that presentation. So if anybody here has any questions based on what Ognian had given or talked about during his presentation, you can let us know. Okay, cool. So question, do you think DeFi users would pay for a service that acts as a monitoring service for when a source code built wasm hash doesn't match the canister wasm hash deployed?
That's a good question. So I know for Ethereum that there exist services that check whether a build is reproducible. I imagine that something like that would be useful. Whether users would be willing to pay for that, that's I can't really answer that, but it would definitely be useful.
Cool. Hopefully that answer was helpful, Saikat. Okay, that was the only question that I saw. So unless anybody has a follow-up question or anything else, I think we can close the call for today. So, okay, so Saikat indicated that the response was helpful. So thank you so much, Ognian, for your time preparing this presentation, for giving this presentation. We will be posting this talk to YouTube shortly thereafter. Thank you, Saikat, for your question. And we will see you all next time at a future community conversation.